spit out and say, look, it can just spit out to you exactly what I did, which is where you called cly at line 2, you didn't call restore flags at line 4. This is bad. You need to fix that. And suddenly it's trivial to actually go and figure that out and patch it. So there's probably at this point there's actually very few people in your building that know how to write code that couldn't fix it. One quantitative measure of this is I taught a freshman seminar at Stanford where we had a bunch of Stanford freshmen run our tools over the Linux kernel. They found a bunch of bugs, and they were able to write patches and submit patches and actually get them inserted in the kernel and running on a bunch of desktops, even when they don't really understand how to write code or they don't really understand what's really going on in the kernel. And if you've ever talked to Stanford freshmen at a technical level, you realize it must have actually had to have been pretty easy for this to work out okay in the end. So the third thing is that it's immediate. So it finds bugs without having to execute the path at all. And this is really nice because obviously the number of paths in code scales roughly exponentially with the size of the code. So if you're looking at a real commercial system, millions of lines of code, even if you're insanely aggressive about testing, you're probably only touching a couple percent, 1 or 2% of all the paths in the code. The nice thing about stack analysis is it can rip through all the code and with clever use of caching, explore all paths. And this is pretty nice. And then finally, the only reason to talk about this is that it's pretty effective. So we find thousands of bugs in Linux, OpenBSD, lots of bugs in commercial systems. I've never seen a big system where you go and you check it and you don't find a lot of interesting stuff. It just doesn't seem to happen. Okay, so there's a couple key things to keep in mind. So one thing is that I'm going to talk about, I'm going to try to keep the talk very concrete by giving code examples. I'll use Linux code examples because we're not going to get sued for it. These types of bugs and these types of examples show up in all the commercial systems we check as well. This is just an easy way to talk about something without getting in trouble. And the second thing is this is a talk that's geared towards tool builders. We'll try to teach you how to build stuff so you understand how things work in a very real way. So when they talk about you write things and you build a checker, probably someone else actually has written that for you. But it's easier linguistically. Okay, so just a bit more detail to see what things actually look like for real. So the checker we had, if you disable interrupts, you re-enable them. The state machine for that is on the right-hand side of the slide. It's a fairly trivial state machine. The initial state is we just assume interrupts are enabled. If you see a call to a disable interrupt function, you disable interrupts to this is disabled state. If you see a subsequent enable call, you can go back to the is enabled state. You can go back and forth as many times as you wish. And there's 3 error states here. One is if you have interrupts enabled and you call enable again, that's bad. If you're disabled and you hit another disable call, that's bad. And if you're disabled and you run out of code, that's also bad. So all 3 of those go to errors. Okay, so fairly simple check. Okay, so the code on the left-hand side is a real checker written in our language. If you're familiar with Lex and Yak, it looks sort of like that, not entirely by accident. So here, it's just basically it's a textual transliteration of the state machine on the right-hand side. So there's 2 states about midway down the slide. There's is enabled and there's is disabled. Every state has a pattern, and we match those patterns in order, and if a pattern matches, you go to the action. So is enabled has 2 patterns. One is this disable, and there's a double arrow to the is disabled state. So all disable is, if you look above that about one couple lines, there's this pat disable equals cly. All that does is it matches when you see a call to cly. Okay, so when we see a call to cly, we're going to go to this is disabled state. Down in the disabled state, if we see something that matches enable, which is either a call to sty or restore flags, we go to this is enabled state and we'll go back and forth. And then the error cases are just as before. The one funny thing is that end of path, which will match when you run out of the code. So there's a couple things to note here. One is that you can actually fit something that's non-vacuous on a PowerPoint slide, given the right interface, which is just if you can couch things in terms of code. You can actually if you compile this checker and you run it in the system, you run it on Linux, you run it on, say, a BSD system, you're going to find a lot of bugs, and the people will actually be really interested and they'll go and fix them. So there's not too many non-vacuous things that fit on PowerPoint slides from bitter experience. The second is that with the right interface design, the programmer has to know very, very little about compilers. They just have to understand their rule, which is you disable things, you re-enable them, and you can write your checker in terms of the code constructs that are important for that disable enable calls. You don't have to understand register allocation, pointer alias analysis, heap analysis, shape analysis, anything like that. You just say, this is what my rule is. You hand that checker over to the compiler, and then the compiler jams it over the source code, doing its own, using its own machinery to push these checkers as far as possible. All right. So we have a couple questions. How difficult is it to implement C++ tools like Scott Meyer's Effective C++? Those are actually pretty easy because those are typically, you don't do much flow analysis. They're, just never do X, or don't ever do Y, or if you do Y, you also better do Z. But there's typically not much path analysis there. So stylistic rules in particular are very low-hanging fruit for this. This talk tends to focus on things that more will crash your system outright than those types of rules, but certainly style rules work pretty well. And have we already implemented them for any customers? So I'll have to defer that to Ben Shelf at the end. I think we have some we have a suite of C++ checkers. I'm not sure what sort of coverage there is for Scott Meyer's, but I'm sure he can talk about that. Okay. So this checker was tying a state to a path. So on this path, interrupts are enabled, disabled. Of course, you also want to tie states to program objects. So a very common sort of don't do X after Y rule is that if you free memory, don't use it. So here the state machine is even simpler. So on the right-hand side, we have this 3-state state machine with 2 arrows. In the start state, if we assume all variables are okay. If you see a call to k3 of v, which means that v is going to be freed, we put v, the program object, in the freed state. If you then see a subsequent use, you give an error. So again, the checker for that is just a straightforward textual transliteration. Here we have start, which is just the start state. If you see a call to k3 of v, where v is this special type any pointer, so it's going to match any pointer whatsoever, whether it's an expression, whether it's a variable, whatever it happens to be, we'll put that expression in a freed state. And then the compiler tracks that if you're in the freed state, there's a couple things you are allowed to do with the variable. So you are allowed to compare it to something else. You're not allowed to dereference it, but you can compare it. People typically will do this on cleanup paths. So we let them do this to get rid of false positives. But other than those two types of comparisons, any other use, which is the next pattern after that, we're going to just give out as an error message. So from the code example, the way this checker is going to work is here the code allocates kmalloc and stores it into ent data, the data field. If that's failed, they're going to k-free ent. So at this point, the checker will put ent in a freed state. They then go to out, the out label, which then returns ent out into the file system. So at this point, a variety of sort of exciting things will happen to you. Probably none of them are very good. So a key thing here is that the compiler does the heavy lifting for you by design. So once you mark that some expression is freed, the compiler will track, well, you said X is free and X gets assigned to Y, so it's also going to know that Y is freed. If you then pass Y to foo, to a function call, it's going to track that thing went across the function procedure boundary. And typically just do these sort of assignment type tracking for you. If X is in some state, it eventually percolates to Y. Y is also in the same state. That way you don't have to do it. Okay. So you can tie states to paths, to variables, and also some rules are contextual. So in certain, you may be able to do a fairly broad range of things in general, and in certain very specific contexts, you're no longer allowed to do those. So one thing that comes up in many systems is you're not allowed to block if you hold the locker and are so disabled. So what can happen to you here is if interrupts are disabled and you go to sleep, there may be no way to wake you up ever again. The whole system may be in a deadlock. Or if you go to sleep holding a spin lock, if the thing that needed to wake you up also needs to require the same spin lock, you have a circularity and you have a deadlock. So this is typically bad. This is definitely something you don't want to do in Linux, and it's also true in most systems. So this checker, you should probably see how to do it already. It's just a fairly straightforward extension of the disable interrupt checker. So what we're going to do is we'll start off in a clean state. If you see a call to lock or disable, we'll go to a no block state.